So the last bit of section 2.2, let me just make sure this is, okay, it's recording. The last bit was section 2.2. It's this thing called the sandwich theorem. And it's just another way of figuring out a limit. Now remember, when we're talking about limits, if we're talking about the value of a function when the x, the independent variable, is close to some value. So it doesn't, have to be equal. X doesn't have to actually be that value. It just has to be close to it. And what the function is doing when x is close to a value versus what the function is doing when x is at that value, those can be two different things. So let me give you kind of a review of what we're talking about here with limits. So let's say we have something like this. So let's say this is 5 and this is 4. And we're at 3. So the difference between a limit and the actual value when x is at some number is at x equals 3, f of x is equal to 4. So this is our f of x. So what we've got a hole here, and then a little part of that hole dropped down, and we've got this right here. So at x, f of x is equal to 4, but near x, get cursive, near x equals 3. So there's at and there's near, two different things. So at x equals 3, f of x has a value of 4. But near x equals 3, f of x is actually equal to 5. And this would be the limit as x approaches 3 of f of x. And this is going to be an important idea, especially when we start talking about infinities. And this might seem kind of silly. Why are we interested in what f is doing near some location instead of at it? And again, when it comes to infinities or infinite processes, this is going to be really important. So that's the idea of a limit. Now, going back to the sandwich theorem, it can be kind of tricky to figure out what a function is doing, depending on what kind of function we're working with. And I'll pull up an example here. I can pull it up on the computer. But let's say we have this. Let's see be an x value and open interval I. So we're going to take a part of the x-axis here. We have C, we have A, we have B, and we're interested in an open interval. So we're not really including A, not really including B. We do have C somewhere in there. And so this would be our interval I. So let's suppose we have the following situation. So let's say we have this scenario. g of x, h of x, f of x is between them for all the x values on this interval. Possibly not at c, though. And I'll look at the situation when this doesn't hold at c. That's a real special case. So this is the kind of situation, we're going to kind of not go with the special case for now. I'll take a look at that a little bit. But something roughly like this. Well, here, let me give you the full theorem, because there's a key point in this theorem that has to hold true. Let me do that first. If the limit as x approaches c of g of x equals the limit as x approaches c of h of x, so as we get closer to c, g of x and h of x have the same limit. Then the limit as x goes to c of f of x, that's also equal to L. This kind of idea is going to come up a number of times. We'll come up with integrals when we get to integrals. And Calc 2, you'll run into this with infinite series. But basically, we have something like this. Let's see. So I've got a situation like this. This is the idea of the Sandwich theorem. That basically these three functions are going to converge. I'm going to make this a little more accurate. They're kind of overlapping here. These three functions are converging, or coming very close to converging at C. So if we know h of x and g of x, these sort of converge to the same limit. Well, if there's something that's between these functions, it's also going to have a limit or converge at that same point. So that's the idea of the sandwich theorem. We're sandwiching f of x between h of x and g of x, and that lets us know about the limit only where the limit of g equals the limit of h. This isn't going to work for, say, around here. Here, the limit of h and the limit of g are not equal. And since they're not equal, can't make any claims about the limit of f. So let me show you the special case. Now let's say at x equals c, this breaks down. Now for for x not equal to c, this has to hold at every value of x in that interval. But let's say at c it doesn't work. So what that looks like is basically something like this. So what I'm going to do, make a little change here. For f of x, what could happen is you could have another hole where f of x has a hole and it could have a value, say up here. So this is how that would break down. Now again, the sandwich theorem actually still holds because the limit is not about what's happening exactly at C, but what's happening near C. And when we're near C, we're up here, and this is near L. So that's the difference. That's that special case. So any questions about that before I do an example? All right. So let me run through the example here. So we want to find this limit, given we have this inequality near zero. So what we want to do, we're going to treat this as g. This will be our h, will just be a constant function. This will be our f. So if we let g of x be that, and again, this is a polynomial. So we take the limit of g of x as x approaches zero. Well, we can use our rules for evaluating limits for polynomials. And so since this is a polynomial, the way we find the limit is, for all intents and purposes, we can treat x as if it's zero. And so this will come out to be 1 minus 0, or 1. And again, it's using that special rule for calculating limits with polynomials. Now for h, well, that's going to be that constant function 1. And then the limit well, again, this is a polynomial, very simple polynomial. And with any polynomial, we just replace the independent variable with, well, the c that we're approaching. And in this case, there's nothing to replace. So this is just going to stay 1. So here's the point. The limit as x goes to 0 of g of x equals the limit as x goes to 0 of h of x, which is equal to 1. And we've been told that near x equals 0, this inequality holds. Now, at x equals 0 is a different story here. If you try to plug in x is 0 into these, things aren't going to work. 0 times 0, x is going to be 0 if we use our polynomial rule. We get 0 on top. This will be 2 minus 2 times 1. Cosine of 0 is 1. So this becomes 2 minus 2 times 1, or 2 minus 2, or 0. So we get 0 over 0. So at this location, at the very least, we have a hole at x equals 0. But that doesn't matter. We don't need the function to exist at the point, the very location where we're taking the limit. We don't need it to exist at x equals 0, just near x equals 0. And we're told our g of x and our h of x have f of x between them near x equals 0. So since this turns out to be true by the sandwich theorem, abbreviate theorem, the limit as x goes to 0 of our f of x that's also going to be equal to 1. So any questions about that? All right. So the last thing to mention is what I would call the inequality theorem. And again, this is one of those things that can be important later on. Abbreviate theorem again. So the inequality theorem. If f of x is less than or equal to g of x for all x in the open interval I, so f is always smaller than the function g on this interval. And again, we're going to have, there's that special case that we're not going to, when it comes to our limit, we're not going to worry about. So there might be some value C, again, just like before, that's in this interval where this happens not to hold at that one point. Then the limit as x goes to c of f of x will be less than or equal to the limit as x goes to c of g of x. So basically, if one function's smaller than the other, well, then the limits, one's going to be smaller than the other. Now, they do make a note in the text, and it's kind of an interesting one. I'll use this as our example. Just because f of x is less than g of x for all x in that interval I, except for possibly just because this is true, where f is always going to be smaller than the function g for all the values x in this interval, except possibly x equals c, this does not mean that the limit is also going to be a hard inequality. And so the thing that we're interested in on this thing is the limits would still be equal. I'm going to show you an example, because basically what this is saying is that it's possible for f of x to intersect g of x at that one point x is c. That's all it's saying. And then for every other point in that interval, they're not equal to each other. And we see that all the time when like lines intersect each other. You have equality at one point, but then every place else, the functions have different values. So the example I'll give, let's see. Let me pull that up here. There we go. So what this is, let's say you have this. So here, let's say we have g of x is the absolute value of x. And then here, we have f of x, which is 1 minus the cosine of x. And we're near 0. So in this case, g of x is always bigger than f of x, except at x equals 0. But if you take the limit as x goes to 0 of f of x will actually equal the limit as x goes to 0 of g of x, which is going to be 0. So that's just a special point they wanted to make in the text. Just because you have hard inequalities at all the other points except x equals c, that doesn't mean you'll have a hard inequality for your limits. That's not going to hold true. Anyway, arrows here. So that's section 2.2. That's that introduction to limits. We're going to try to get precise now. What we've done so far is we've had this sort of vague idea of being near something. A limit is what a function does when it's near something. And we want to talk about something a little more mathematically precise, because with math, we're usually dealing with numbers. We have decimals, we have very specific things that we're doing. The word near is kind of fuzzy. So can we be more precise? And there actually is a way we can. Well, perhaps an improvement. So I'm going to go through an illustration, just kind of talk about what we're getting at here. Let's say we have this. We're going to study a limit. So let's say f of x is some function. And when we get close to x equals c, f of x gets close to this value L. So let's say we want this. So now we're going to get precise. We want f of x to be near L or close to L. What does that mean? Well, let's attach a number to it, or a symbol for a number. So specifically, within epsilon units of L. What epsilon is, I'll give you a second to write that down and talk about epsilon. This is where we got to kind of slow things up a bit. Maybe not too much, but at least talk about what epsilon could mean. Epsilon's a symbol that we use. It's a Greek letter, and we use it to represent pretty much as small a number as you were thinking of, or as small a number as you want. So it's usually any small number you want. And you could make epsilon be something really small, like the number 1. Sometimes people choose an epsilon equal to 1, or an epsilon equal to 0.01. So some examples of epsilons. You could see epsilon equal to 1, epsilon 0.001. Give me a second, I gotta look this one up. Let's see. You can make epsilon very small. If you take physics, you'll run into this. So about, we'll estimate 6.626 times 10 to the negative 34. That's a small number. That's Planck's constant, by the way. So very, very small number. The point is epsilon is just something really small. And so when we talk about f being close to x, I'm sorry, not x, f of x close to some limit value, L, we're saying that we want it to get really close to L. It doesn't actually necessarily become L, but it gets very close. We can make it as close as we want it to be without actually being L. So epsilon, arbitrarily small number. That's the idea. So we want f of x to get really close to L. So all right, so what do we do with this? So what does this look like in our graph? Well, it's going to look like this. So we've got our function here. C. Here's L. And so L plus epsilon could be up here. L minus epsilon will be right here. Here, let's lower this a little bit. That's better. So what this does this is the part of our function, f of x, that has y values that are somewhere between L minus epsilon, L plus epsilon. So that means the distance in here, epsilon, epsilon. So we've got f of x. If f of x is within epsilon units of our limit, f of x is somewhere in here or somewhere in there. There we go. So that's the idea of getting f of x close. You come up with some epsilon and you say we're interested in f of x being within epsilon units of L. Now, the next question we're going to ask is, okay, great, you can get f of x close to L, but for what x values does this happen? So this is sort of the burning question. So to figure that out, what we're going to do, I'm going to make some alterations here. We're going to take our graph. And we're going to extrapolate this like so. So we drop these down. And what we find is this. That green area gives us the x values that place f of x. X values here will give us function values that will fall between epsilon plus L and then L minus epsilon. So I'm going to call these two parts D1. I'm going to call this one D2. Well, D2 is bigger than D1. But the point is going to be this. These values of x result in L minus epsilon less than f of x less than L plus epsilon. So questions about that so far? Now we're going to make kind of a, it might seem like a slick observation. So D1 is smaller than D2. So what we're going to observe is this. If the points all in here will give us f values that are between L minus epsilon and L plus epsilon, well then also values that are only about to here, which says the length of D1, but on the other side of C, those will, of course, still will give you values of f of x between L minus epsilon and L plus epsilon. So let me put it like this. If it's hard to see this, let me know. So this is what we're going to do. We're going to shrink this D2 to something the size of D1, but we're still staying close to C. So we're doing this. And again, all these x values are going to give us function values that are still going to be giving f of x between L minus epsilon, L plus epsilon. So that's what we got. So where are we going with this? Well, let's bring it all together. So what we're going to do, we're going to call D1 we give it a special name. We call it delta. And so what we'll say is this. If our x values are between C minus delta and C plus delta, for x values are between here and here, then f of x will be between limit minus epsilon and limit plus epsilon. Or put another way, if we have x values within delta units of c, f of x will be within epsilon units of L. And so this is the idea of a limit. We want to identify, once we decide how close we want our function to be to L, we're going to search for the x values, the interval of x values that allow this to happen. So how does this work in practice? Well, let's go back to what we've got here. We have C minus delta less than x greater than C plus delta. So again, if we're choosing an x value in here or in here, then as a consequence, L minus epsilon is less than f of x less than L plus epsilon. Now we can rephrase this. Let's say we subtract C from up here and L from here. And let me give you a second. Any questions? Any questions before I continue on? Because now we're going to do some algebra. We're going to come up with a kind of a slick trick here. It's going to give us a definition of limit. So what I'm going to do, I'm going to subtract C. And when you're working with compound inequalities like this, I got to subtract C everywhere. Same thing with this one. Subtract L. And so what you get? Okay, fair enough. Now, it might have been a while since you've seen this, but this is an old trick from algebra. Note, the absolute value of u less than d means negative d less than u less than d. It's an old trick from algebra. They mean the same thing. You can start with this and you can get that. So what we're going to do is we're just going to go backwards. If we've got this, we can rewrite this as that. So again, if you haven't seen this for a while, it's okay. Welcome to calculus. It's one of the best places where you can review your algebra. But this is an old idea from algebra. If you've got this, you can rewrite it as this with an absolute value. If an absolute value is something less than a constant, you can break up that absolute value like that. So using that trick, what this will become, x minus c less than delta, then f of x minus L is less than epsilon. We're putting it into words. If, remember, absolute values tell us distance. So the distance between x and c, and if x is smaller than c, like x is 2 and c is 3, well, I mean, it's still a distance of 1. 2 minus 3 is negative 1. Absolute value of negative 1 is 1. So the distance, if the distance between some x value and c is smaller than delta, well, then the distance between f of x and the limit L will be less than epsilon. Or put another way, if you're within delta units of c, f of x will be within epsilon units of L. So we're finally there. We're finally sort of just burrowing our way through all these ideas until we basically just come up with a sort of a, hopefully, relatively simpler explanation. If you're within delta units of c, then f of x will be, if x is within delta units of c, then f of x will be within epsilon units of L. So here's the actual formal definition. Remember, you get to choose epsilon. And this is what is the definition of the limit as x goes to c of f of x equals L. So that's the definition of a limit in more precise terms. Now, questions about that? Now, the power behind this definition is we generally choose epsilon first. And then we're going to search for a delta that makes this epsilon true. In other words, we're going to choose an epsilon. We want to find f of x to be really close to L. We could let epsilon be 1. It could be 0.001. It could be Planck's constant. But we want epsilon usually to be something. We kind of assume epsilon could be arbitrarily small. Well, given that fact, can we find a delta that makes this epsilon work? Can we find a delta where, when x is within delta units of c, f of x will be within epsilon units of the limit? So it all kind of starts with your choice of epsilon, and then you find delta. So let's take a look at this. Let's do an example. Now, I'm going to do some symbolic examples. And the thing with the symbolic examples, there's two things to keep in mind. You're going to sort of run into two approaches to these, where I'm using epsilon strictly as a just something you could just choose. And then I'm going to do another example where we actually specify epsilon as a number. So let me go through an example. We want to show that the limit as x goes to 1 of 5x minus 3 is equal to 2. Now this whole showing thing, I'll be honest, this is kind of weird. You're getting to what's called math proofs. Math proofs, it's okay to use theorems to show something is correct, and you've learned that in geometry. This is a way of showing limits are correct, and the idea is that we're going to find a relationship between delta and epsilon that no matter how small we choose epsilon, we're always going to find a delta that lets this epsilon be, well, we can get f within epsilon units of the unit, of the limit. So there's a basic procedure to this. Let me show you how we're going to do this. Well, first, choose epsilon greater than 0. Now, I might not actually choose this. I might just say, well, I'm just going to let epsilon be any tiny number bigger than 0. And okay, that's good enough for me. Then we'll look for delta. We're going to choose epsilon, and then we're going to look for delta. So one of the key things in these types of problems is to use the definition of the limit. We kind of need to know or have an idea what the limit could be. So what we're going to do, we're going to use our polynomial properties and guess the limit. So let's see. We have a strong belief that the limit as x goes to 1 of 5x minus 3 equals 2. So we're going to use this as our L, and we're going to see if this is going to make sense. So that being the case, let's go through our beginning of our procedure. We're going to choose epsilon greater than 0. I'm going to do it fairly simple. I'm just going to say let epsilon be greater than 0. And you can come back later and replace epsilon with some number. So what we're going to do, we want to find x, or f of x, between limit minus epsilon or limit plus epsilon. So we're assuming that L is equal to 2. We're going to see what this assumption does. So let's find out what's going to happen here. So if we assume L is equal to 2, then this would mean that f of x minus the limit that we're guessing is less than epsilon, or 5x minus 3 minus 2 is less than epsilon. We're assuming this is true. Now, this is a trick in mathematics you'll run into where we assume something is true and see if it actually holds out. For example, if you want to see if your car runs on grass clippings, it doesn't. But let's say you wanted to test this empirically. So you would assume, very dangerously, that it does, and you would take grass clippings and you would just, you shove them into that gas tank, and then you would turn the key and see what happens. And nothing's going to happen, and who knows, you could do enormous damage to your car. So let me make just sort of a declarative thing here. Don't put grass clippings in your gas tank. Don't do it. No, don't even think about it. So that is one way to go about the world, a very dangerous way of going about the world, I'll admit. But in math, since we're living on paper, we can afford to live dangerously on paper. So we're going to take this function, this possible limit, and we're going to assume that if you subtract the function and the limit, you're going to be within epsilon. And you can make epsilon as small as you want when we're close to x is equal to 1. So this is the setup. We've got our epsilon, and if that's our epsilon, this is our guessed limit, and here's our function. Hopefully this doesn't blow up on us. So how do we test this idea? What's going to be the equivalent of turning the key to see what happens? So what we're going to do is this. Given the above, that stuff up here, our guess, and given c is equal to 1, we try to identify the delta. So I'm going to try to figure out this delta. So again, if being close to x equals 1, we believe this is true, that the difference between the function and the y value of 2 can be arbitrarily small if we're very close to x equals 1, we should be find a value of delta that gives us sort of a domain of x values above 1 and just below 1, where this is still going to hold true. We'll find out. So, all right. So we're going to start with this. So this is one way of going about these problems. 5x minus 2, minus 3 minus 2. We're going to try to solve. So I'm going to call this approach number 1. Solve for x minus c less than delta. In fact, I'm not going to put less than delta. I'm going to say solve for x minus c. And then what's going to happen, what pops out on this other side, that tells us our delta. So solving for x minus c. Well, this will simplify down to 5x minus 5 less than epsilon. Now remember, c is equal to 1. So if this is true, well then this is true. And then we can factor out a 5. We can factor this out of the absolute value. And divide by 5. And we get our absolute value of x minus c. So questions about that? So what we've done is we have this. So we have f of x and L. And now what we have from this, we get x minus 1 less than epsilon over 5. So this is c. So what must this be? Well, this must be delta. So we found our delta. Questions about that? So how do we write up our answers for this? Well, this is how it goes. So for any epsilon greater than 0, there exists delta equal to epsilon over 5 such that and that's how we write our answer. So what this is saying, remember, we can make epsilon as small as we want. So no matter how small you choose epsilon, however close you want f of x to be to the value of 2, just choose a delta of epsilon over 5. Let's see. It's kind of hard to see here. This is C plus epsilon over 5. And this one, C minus epsilon over 5. So the funny thing about this one, to make this work, what you have to do is, in fact, here, let me change this. Instead of C, we're going to do some board surgery here. Let's call it 1, because that's what it is. So we have 1, 1, 1. This one, of course, is going to be 2. So basically, if you're within epsilon over 5 units, a fifth of an epsilon within the number 1, you'll be within epsilon units of number 2 for f of x. So questions about that? All right, I'm going to do another one. Now this one uses a slightly different method. Now these take practice. They're kind of a logical sort of game, and they're kind of fun once you get the hang of them. But they do take practice. So let's say we have this. Prove that the limit as x goes to 5 of the square root of x minus 1 is equal to 2. So we're going to do the same thing. We're going to start out with f of x square root of x minus 1 L is equal to 2. We're just going to see if this works. So we have f of x minus L less than some epsilon. We just choose epsilon, arbitrarily small. And we're going to try to look for x minus c. We're going to do it kind of in an unusual way. So we plug this in. We have this. Now we're going to do that trick from algebra. We're going to break this up. And our goal, again, is we're looking for this x minus c. So we're going to start with this. We're going to try to come up with this. We're going to break this up. Like so. We can add 2 everywhere. So we'll get minus epsilon plus 2 less than the square root of x minus 1 less than epsilon plus 2. We can do that. And of course, 2 plus minus 2 is 0. Now, when we have things like this, we're going to make kind of an assumption. Again, this is an algebra trick. Let's assume epsilon is less than 2. So for this to work, let me see, let me double check this. Maybe this isn't important. Maybe this will be fine. I just want to make sure. Can't get in any sort of trouble with this. Okay, we should be all right. We should be okay. So what we're going to do, we're going to square everything here. I'm just being pedantic. I'm going to square everything through here. Why I'm being cautious is that this idea of something smaller than this, smaller than that, you can just square everything and the inequalities don't change. This isn't always true. Like if this was, say, -10, this was +1, and this was +2. If you squared -10, you get +100. Squared 1, you get +1. Squared 2, you get +4. So this would break down, but we, for a very, at least for a small epsilon, are going to be okay. And then just looking at these two inequalities here, just making sure that's going to be all right. We can go ahead, especially if it's a very small epsilon, you're going to be okay here compared to the number 2. So going ahead, squaring. And now I'm going to get to what I call approach number 2. And this might seem kind of unusual. Instead of looking for the absolute value of x minus c or x minus 1, what we're going to do is, and technically you can argue you're squaring a square root, but well, anyway, what we're going to do is look for x. So we're going to switch gears. Instead of looking for x minus c, we're going to just look for x. So this is another way of doing this. So what we're going to get is negative epsilon plus 2 squared. We'll add 1 to both sides. Epsilon plus 2 squared plus 1. And so this here, we're going to hang on to this for a second. So the way the second trick works, let's think about in this case, our c is equal to 5. So what we're doing, we're trying to show that x minus 5 is going to be less than some delta. We're looking for this. Or negative delta x minus 5 less than delta. Add 5 to both sides. And so we have a statement for x. So we have 2 statements for x. So now we're going to compare these. Well, when we do that, this is what we've got. Negative delta plus 5 must be the same as this. And then for b, delta plus 5 is going to be equal to this. Now, if you remember, at the beginning of the lecture, we had this thing with D1 and D2, where on the x-axis you had a D1 interval, and then there's a larger D2. If you want to take a second to flip back in your notes, take a look at that again. Well, we're going to try to do the same thing. Take a D2 and shrink it to a D1 in this approach. Because what's going to happen, we have two different statements for delta. We're going to solve for delta in both of these. The smaller one will be our D1. The larger is going to be our D2. And we're going to choose the D1 representation for delta, the smaller one. So using that trick, let's work with this. So for A, we get negative delta plus 5. We'll FOIL this. We get epsilon squared minus 4 epsilon plus 4 plus 1. So these will add up to 5. Subtract 5 from both sides. We're going to get negative delta is equal to epsilon squared minus 4 epsilon. And then multiply through by negative 1. We get delta will be 4 epsilon. Negative times negative is a positive. Negative epsilon squared. So that's our first delta. Now, is it D1 or D2? Well, we got to compare it to the other value for delta that we're going to come up with here. So for B, delta plus 5, epsilon plus 2 squared plus 1. Again, we're going to FOIL. And again, these add up to 5. We're going to subtract 5. We'll get, and then they're both positive, so we can just call it 4 epsilon plus epsilon squared. Or epsilon squared plus 4 epsilon, either way. But writing it like this, we can see 4 epsilon subtracting something, 4 epsilon adding something. What's going to be larger? And again, we're making an assumption that epsilon's a very small number, usually no bigger than 1. Usually it's very small. So the thing with this is, either way, the D1 is going to be this, and this is going to be our D2. So the larger interval, the smaller one. So we're going to let delta be the smaller one. And there we go. We found our delta. So now I have to write up our solution. And so the solution we're going to write up is this. Proof. So this is how we're going to state our answer. For any epsilon greater than 0, there exists delta equal to epsilon minus epsilon squared such that And we're within delta units, and there's our delta, of 5, f of x is within epsilon units of 2. That's going to be our answer. Questions about that? So I have one more example, and this one is when we actually specify epsilon. We're going to choose epsilon equal to 1. And again, we're going to run into that situation where we have to choose between a D1 and a D2. So I want to prove that the limit as x goes to 23, oh, sorry, don't need any absolute values there, of the square root of x minus 7 is equal to 4 for an epsilon equal to 1. So we're going to start out with this. F of x minus L less than epsilon. Or square root x minus 7 minus 4 is less than 1. Now we have a value for epsilon. So we're going to try to find x minus 23. We're also going to use the second approach. So we're going to look for x minus 23, and then ultimately we're just looking for x. So either way, we'll probably pass through this as we go to x. So in fact, you don't have to look for x minus 23. You can cross this out. You cross that part out. We're just going to look for x. So we're starting with this. Now again, we're going to break this up to minus 1 and 1. We could add 4 to both sides. We have minus 3 less than square root of x minus 7 less than 5. Square root everything. 9 less than x minus 7 less than 25. Add 7 to both sides. 16 is less than x less than 25. Oh, 32. So again, we can use this approach number 2. Now, x minus c is less than delta, or negative delta is less than x minus c less than delta. Add c to both sides. So negative delta plus c is less than x, which is less than delta, plus c. Now in our case, c is 23. So that's going to give us negative delta plus 23 is less than x, less than delta plus 23. So we're going to compare these two. And we're going to get a D1 and we're going to get a D2 ultimately. So first off for A, negative delta plus 23 equals 16. And for B, delta plus 23 equals 32. So solving for A here, we're solving the problem in A. Subtract 23 from both sides. Negative delta is negative 7. Multiply by negative 1 all the way through. Delta is 7. So now let's take a look at part B here. The other possible value for delta satisfies this. Subtract 23 from both sides. Delta is equal to 9. So this is our D1, and this is our D2. So again, we're going to let delta be the smaller of the two. We're going to let delta be 7. And so this is how we're going to write up our answer. Remember, our C is 23. And our L is equal to 4. Oh, sorry. So what it's saying is this. If X is within delta units of 23, or put another way, if X is within 7 units of 23, then f of X will be within 1 unit of the number 4. And that's it. Questions about this? I know this section can be kind of tricky. If you have any questions, let me know. I've extended some of the homeworks, by the way. Again, 2.1, 2.2 are due Wednesday. This homework is due next Monday. So you have a weekend to work on it. But again, any questions that come up with this, let me know. And it takes practice. It's kind of a funny thing to work with. But there's basically 3 techniques that we've really kind of looked at. Or really 2. The first one we did where we found that epsilon over 5. You could just solve for the absolute value of x minus c directly. And that's going to work when you don't have like a D1 and then a larger D2. That approach is going to be fine. But if there's a possibility you could have like a D1 and a larger D2, this second method where we solve for x using deltas and c's, and we solve for x using epsilons, and you compare the sides, that's probably one of the easier ways to go. So at least that'll That's a very good method to go, especially if you could suspect you're going to get a D2 and then a smaller D1, and you have to choose between the two. So that second method isn't a bad way to go at all. So anyway, that's it for today. We'll finish 3 minutes early today. So again, any questions about this, let me know. I might try to do maybe an example on Wednesday just to kind of go through this again. But we'll jump into 2.4 and hopefully 2.5 on Wednesday, where we look at one-sided limits. Basically, what is a function? How is it behaving as you approach an x value from the left versus approaching from the right? You can get different behaviors, actually. So we're going to look at that on Wednesday and hopefully get into some continuity, section 2.5. But other than that, that's it. Have a wonderful day. Again, any questions, let me know. And yeah, that's it. A wonderful afternoon.